So this is a lecture on the analysis of variance, and this is often a very difficult um, concept for students to grasp because it asks you to do a lot of calculation. I would tell you, I know almost nobody who knows how to do the calculations for the Anova. It is such a common statistical test that people put their data in a stat package and just push run. It computes the values for you. In introductory statistics, we like you to see behind the scenes why certain things work instead of just showing you. Again, most of the people that I know have forgotten why it works, but they understand what it's doing. And what the Anova is doing is taking four groups. I'm not sorry, it's usually two or more groups. Here we have four groups. And asking a question, are they different from each other on some value that they have been measured on? So here is some way of learning words, and each of the group represents a different strategy that somebody used to try to remember the words. These are the number of words that they recalled, and each line is a different person. Okay, so there's six. Well, there doesn't have to necessarily be the same person in each column, but however many participants there were six here, there were six here, 24 participants. Okay, so how would we answer this? Well, what the analysis of variance does is to really ask this question. There is some variability within groups. So for each group we can figure out what the variance is within each group, and then we can do a variance between groups, and then we can do a variance for everybody. And what the idea is if these numbers are randomly generated and there's no pattern, then the variance within groups will equal the variance between groups, and there will not be any difference because the numbers just randomly occur. But if there is a difference between the within group variance and the between group variance, then we say, the reason for that is because there's differences in these groups. Now, in working through your worksheet, you have to do a lot of computations. And the very first thing that you're going to do is just find the mean of these values, which here number 40 is what we did. Then we just sum up the totals that we have. Then we get a grand total of all of these values. I don't see the grand total reported there. And then we're going to find a grand mean. We're going to find the sum of squares for all of these. The sum of squares would be squaring each value and adding them up. We're going to get a grand mean, which is adding up all of the values and dividing by 24. And that's what you're doing at each step. So I sort of show you how to do some of these steps. I did it in Excel. It's very easy to do in Excel step by step. There's my means. I just said, okay, find the mean of those 6 values. Here's my totals. Just add up those 6 values. Here is the mean of all the means. Here is where I squared my 6 values, and that is where I added them up. Okay, and this is the sum. This is the sum of squares for each column as well at the bottoms here. Okay, there's all these various steps that have to be done. You just need to know what they are. Okay, we have that. We have the means of what do we do here? We have our values. We have, hold on a second. We have some more deviations from the grand mean. So 3 minus 9.63 is negative 6.63. Then we square that value. Then we add up the sums of squares for each column. We get some grand sum of squares. Keep working. This was the sums of squares total. That's a value we use to compute our statistic. So here was the 319.63. Again, we found the grand mean. We took each value, found the difference between the value and the grand mean. We squared it, and we found the sum of squares total. Okay. Now we're going to do it for sums of squares between groups. I'm sorry, I meant to say within groups, sums of squares within groups. So we found the mean for each group. We found the deviation score for each element in a group against its own mean. So 3 minus 5.33 is negative 2.33. 8 minus 5.33 is 2.67. Then we're going to square those values. We're going to add up the sum of squares in each column. We're going to get our total for all of the sums of squares within groups. I don't think these page numbers are correct anymore. Finally, we're going to do sums of squares between. And that is not easy to do conceptually, but it's very easy to do practically. You just take the group mean, subtract the grand mean for all of the groups, square it, multiply it by the number in there, and you're going to get this value, 219.80. And what we should know is that the sums of square total has two pieces to it. One of them is the sum of squares within, the other is the sum of squares between, and they do add up to equal each other, and that's our check. Now this is the table. This is the table that you really need to know. Okay, what is our table? Well, it's our I had to stop and change these values in here because you will often see different names than between and within. I had groups in error in here, I think, which is what is most commonly used. But the way they're done in the book, we have between and within. And what we're going to do is compare our sources of variability. The between and within sums of squares should equal the total sums of squares. In other words, the total sums of squares is partitioned into two sums of squares, between and within. And here's those values here. We computed 219.8 sums of squares for between, 99.83, and we end up with a total sums of squares. Now, we have to get those values. That's what the computation is all about. Again, I'll just remind you that in standard practice, nobody ever does this by hand. But you do it by hand so that you know how to read this table. And the part of the table we're really interested in is right here, and we just need to know how to get to this value, what's done. Okay, so we have sums of squares that we just computed. We can do that with our raw data. And now we're going to take our degrees of freedom for between. What is our degrees of freedom for between? There were 4 groups. Our degrees of freedom is 4 minus 1 is 3. And we're going to get our degrees of freedom for within. And there were 24 people. There was 4 degrees of freedom, 4 groups. Our degrees of freedom within is 20. And the sum is 3 plus 20, 23. And here degrees of freedom total is just the number of people minus 1. Okay, each of these values is very important. This value is important because it checks on these two. These two values are very important because They give us these two values over here called mean squares. What is a mean square? A mean square is the sum of squares divided by the degrees of freedom. So the mean square for between is 219 divided by 3, 73.3. The mean square for within is 99.83 divided by 20, 4.99. Now here is the idea. If the numbers are just random, they just randomly occur, then the mean square here for between should be equal to the mean square for within. Here we see that this is many times more greater than the mean square for within. And that suggests that the difference between groups is much different than the difference between scores within groups. And that suggests an effect for how you memorize the words. The difference between groups is much different than the difference between within groups. Okay, let me say it again. The difference between groups is much different than the differences within groups. The numbers vary much more between groups than they do within each group. And that is what the F statistic tells us, is what's the ratio of between to within. And here it's 15, 14.69. Okay. Now, I know that that's a large number. You don't necessarily know it's a large number. And so you have to look up the tabled value, the critical value of F. And the question is, what do you need to know to find the critical value of F? Well, you have to know the degrees of freedom between, the degrees of freedom within. You have to know what your alpha is, traditionally 0.05. You have to know, well, that's it. So let's look. Here's critical values of F. And then we find degrees of freedom in the numerator. We find degrees of freedom in the denominator. Let's go back and just see what that is. This is the numerator, 73.3. We're going to divide by 4.99. This is the numerator. This is the denominator. The degrees of freedom in the numerator is 3. The degrees of freedom in the denominator is 20. So 3 degrees of freedom in the numerator. Okay. And we've got to find 20 degrees of freedom in the denominator. And here it is right here. 3.10. That is our critical value of F. It's our F critical. And what it says this, when the null hypothesis is true and all those numbers just occurred by chance, we'll see F ratios as big as 3.1. So your F ratio must be very much larger than that, or just any larger than that, to conclude that the numbers didn't happen just by chance. Of course, the larger the ratio, the more confident you are in rejecting the null hypothesis. So here's our test. We compare our F observed to our F critical, and our F observed is very much larger than our F critical, so we reject the null hypothesis. There's a word we use called significant, meaning the results are significant, meaning they did not occur by chance. It's significant. There's some significant relationship there that perhaps we can find some truth in. Okay, that's it for the Anova.